Hi everyone! So in this video, we're going to be starting a new chapter in our textbook. So chapter 4, and that's what we'll be focusing on for the rest of the quarter, is about exponential and logarithmic functions. So we're going to start with exponential functions, and this video is going to be just kind of a basic introduction to what exponential functions graphs look like. But before we can get into graphing exponential functions, we need to review some properties of exponents. Just because, you can't really evaluate exponential functions if you don't know how to apply exponents to different types of numbers. So you may have at some point in your mathematical career, learned a bunch of different exponent rules. So we're not going to be going over all of the different exponent rules that are out there. We're going to focus on some of the more kind of basic ones for now, and then in a later video, we'll go over some other ones. Okay, so the first one is the very most basic, most kind of essential thing to know about exponents, which is what does it mean to take a number and raise it to a whole number power? So what does it mean to do something like 2 to the 5th power? Well, it just means that you're going to take whatever that base number is and you're going to multiply it with itself a bunch of times. Specifically, whatever that exponent is, that's going to tell you how many times you're multiplying it with itself. So an example of that would be, like I just said, 2 to the 5th. So what is 2 to the 5th? That would be 2 times 2 times 2 times 2 times 2, right? 5 times. And so if you multiply this together, 2 times 2 is 4, times another 2 is 8, times another 2 is 16, times another 2 is 32. So 2 to the 5th is equal to 32. Okay, so next rule. Sorry, I was just trying to debate which rule to do next. Let's do this one next. So what about if instead of taking a whole number, like 2, and raising it to a power, now you're doing it with a fraction? So let's say you have a number that can be written as a over b, and you're raising that number to the nth power. Well, that basically means the same thing, right? It means that you're taking your fraction and multiplying it with itself n times. So it really means the same thing, but there's kind of a nice shortcut for how we can think about that. So what happens when you multiply a fraction with itself, or with any fraction? Well, you multiply numerator times numerator and denominator times denominator, right? And so what that means is that you're going to get a times a times a n times, which is a to the n. And then in the denominator, you're going to get b times b times b n times, and so it's b to the n. And so one way of kind of thinking about it, or one way I've heard people describe it, is they say that the exponent distributes to both parts of the fraction. I don't know if that's necessarily the best way to describe it, but if you just go back to what it really means to take a fraction and multiply it with itself, you should see, why the rule works the way it does. So for example, if you had the fraction 2/3, and you wanted to raise that fraction to the 3rd power, well, that would mean you're doing 2/3 times 2/3 times 2/3, so that would be 2 cubed over 3 cubed, and that would be equal to 8 over 27. Okay, so next thing, so this example that we just did was about what happens when the base, when the number that you're raising to a power is a fraction. Next, we're going to talk about how it works when the exponent is a fraction. So let's say you're taking a number a and you're raising it to the m over n. So I'm using m to represent the numerator of the exponent and n to represent the denominator of the exponent. So what that means is that you are, and there's actually 2 different ways to write it, so I'll write it both ways. The kind of most common way to think about it would be that you are taking the nth root. So the number in the denominator always tells you what kind of a root you're taking. And then the numerator, that number m, that tells us what power we're raising a to. There's another way of writing this that I'll show you an example where it actually makes it a little simpler. Another way of thinking about this is you can take the nth root of a and take that whole thing and raise that to the m, and you'll get the same answer either way. Let me just scooch this over a little bit. But the important thing to remember is that the denominator tells you what kind of root it is, and the numerator tells you what kind of power it is. So an example of this would be something like 8 to the, actually let's start with a simpler example. Let's say 16 to the 1/2. So what would 1/2 mean as an exponent? Well, that would be, the denominator tells us the root, right? So it's a square root because it's 2. And then the numerator is just 1. And so that means that we're not raising 16 to any power. It's just 16 to the 1. And so this would just be the square root of 16, which is 4. So basically, if you just have 1/2 or 1/3 or 1/4, that's just the square root, the cube root, the 4th root, etc. Okay, what about if we have something now that's a little more complicated? So something like 8 to the 2/3. So there's two different ways of doing this. One way is you can take the square root. So I'm going to put a 2 here, even though you don't really need it. And I guess I'll put it here too, just to kind of remind you where that square root came from. So you could think of this as being the, cube root of 8 squared. So that would be the cube root of 64. So personally, I wouldn't necessarily know that off the top of my head. What does it mean to take the cube root? It means that you're looking for a number that when you cube it, you get 64. And so the answer is 4, but that's not one that you necessarily would have memorized, right? But if you think about it, 4 times 4 times 4 is 64. Another way of doing this, I just want to show you, that's actually in this case a little easier. So if we think about it that second way, so if instead of first squaring the 8 and then taking the cube root, if we first take the cube root, so the cube root of 8, and then square it. So what is the cube root of 8? Well, that one's a little easier, right? The cube root of 8 is 2. And so we have 2 squared, and 2 squared is also 4. So you get the same answer either way. It doesn't matter which way you think about it, but I just want you to be aware that that basically there are two different ways of thinking about a fractional exponent. Okay, so last one is a negative exponent. So this is, I think people tend to mix up fractional and negative exponents the most. So what does it mean to take a number and raise it to a negative exponent? So again, just like the one above, there's actually two different ways of writing it down. So the most common way of thinking about it is it's going to be 1 over whatever your base was, whatever that original number was, to the positive of that exponent. So let's just do a quick example, and then I'll show you a different way of writing it down. I guess I'll do this example below. So for example, let's say you wanted to raise 3 to the negative 2. You could write that as 1 over 3 squared, which is 1 over 9. So basically a negative exponent just means that instead of raising your original number to that power, you're doing 1 over your original number to a positive power. Another way of writing this would just be 1 over a to the n, the whole thing. Right? Can you see how those are equivalent, right? If you have 1/2 cubed, that's the same as 1 over 2 cubed. So these two things are equivalent. The reason that this second way can sometimes be more useful is that if you think about it, 1 over a is just another way of saying the reciprocal of a, right? That's a good fact to be aware of. 1 over a number is just another way of saying the reciprocal of that number. And so the reason that can be handy is, let's say that now you're doing a fraction to a negative power. So let's say we have 1/2 to the negative 3. So there's two different ways of doing it. So let's first do it actually the way we did the first one. So the first way that we can do it is we can just say 1 over 1/2 cubed. Right? That's what we did in the previous example. We just took our original base, we moved it into the denominator, and we made the exponent positive. And so this would be 1/1/8, right? Because 1/2 cubed would be 1/2 times 1/2 times 1/2, which is 1/8. And what's 1/1/8? It's 8. But what I think is a slightly easier way to think about that is, okay, 1/2 to the -3. We said that another way that you can do it is you can just take the reciprocal of your original base and raise it to that positive power. And so instead of doing 1/1/2, we can just take the reciprocal of 1/2. So what's the reciprocal of 1/2? It's 2, right? 2/1, which is just 2. And what is 2 cubed? Well, 2 cubed is 8. So we got the same answer both ways, but I think the second way is a little easier. So we'll get to an example in this video where we'll be doing an exponential function where the base is a fraction. And I just think when we get to the negative exponents, if you can think about it this second way, you're going to have a much easier time. And maybe let me write one other thing out here, which is that, it's really about taking the reciprocal, right? So the reason it became 2 is because the reciprocal of 1/2 is 2/1. Okay, so that's all the different kind of exponent properties that we're going to need for this video. Okay, so what is an exponential function? So an exponential function is a function of the form f of x is equal to a to the x, where a is a positive real number, and additionally, a cannot be equal to 1. So this idea about a being a positive real number and a cannot be equal to 1, we're going to come back to that. So I'll make a note about that later on this page so we can understand why that restriction is there. But first, I just want to get a little bit more kind of familiar with like what an exponential function could look like. So what are some examples of exponential functions? Well, one example would be f of x is equal to 3 to the x. Another example would be g of x is equal to 1/2 to the x. Another example would be h of x is equal to 5.81 to the x. So really the base, that number a, can be any real positive number. It can be a fraction, it can be a decimal, it can be a huge number, it could even be 100 to the x. It doesn't matter what that base number is, but the only thing that needs to be true is that it has to be a positive number, and it can't be 1. And again, we'll get to why that is in a little bit. So one thing that I just want to kind of point out that is useful to compare these functions with functions that we've seen in the past is kind of what is the difference between an exponential function, versus what's called a power function. So we haven't used the word power or the term power function that much, but we did talk about this towards the beginning of the quarter. So a power function is a function like g of x is equal to x squared or x cubed or x to the 4th. So a power function is basically a very simple polynomial where it's just x to a power. So that x squared, that's an example of a power function. So what's an example of an exponential function? Well, 2 to the x would be kind of a similar looking example, which is a exponential function. So my question is, like, what's the difference? If you had to describe essentially what is the difference between these two functions, how are they different? Because they look really similar, right? They both have a 2, they both have an x. How would you describe to someone what the difference between them really is? So the main difference is where that variable is, right? Like, so for this one, for the first one, the exponential function, the base, so meaning the number that's being raised to the power, the base is fixed, right? The base doesn't change. It's always 2. Whereas the exponent is going to vary, right? Because that's where the x is. The x is in the exponent. Whereas this example, the second one, well, now the base varies, right? The number that is being raised to a power, that's going to change because that's where the x is. Whereas the exponent is fixed, right? The exponent is always 2. So another way of thinking about it is, for the first one, you're taking 2 and raising it to a bunch of different powers, right? Whereas for the second one, you're taking a bunch of different numbers and raising them all to the second power. So let's just make a quick table just to really kind of drive home like what the difference is between these two functions. Okay, so for example, let's just plug in like 3 numbers, 1, 2, 3. Okay, so what would it look like to evaluate this first function at 1? Well, that would be 2 to the 1, right? And 2 to the 1 is equal to 2. What about when we plug in 2? Well, that would be 2 squared, and so that's equal to 4. And what about when we plug in 3? That would be 2 cubed, which is equal to 8. So notice if we look at these 3 different places where we're evaluating, it's always 2. It's 2 being raised to different powers, 2 to the first, 2 to the second, 2 to the third, etc. Whereas if we fill out a table in the same way for this x squared function, well, now it's going to be 1 squared, which is 1, and 2 squared, which is 4, and 3 squared, which is 9. So in the second example, the thing that's changing is the base, whereas the power always stays the same. And one thing you might notice is that they both share a point, right? Like if we compare here and here, but that's just because that's where the base and the exponent happen to be the same. All the other points are different from each other. Okay, so that's the general idea about what an exponential function kind of looks like. So I want to now quickly mention, why is it that a has to be a positive real number, and why is it that a cannot be 1? So let's address that down here. So why can't a be a negative number? Why can't a be 0, right? Because 0 is also not a positive number. Oops, why can't a be 0? And then finally, why can't a be 1? And just to be really clear, what I'm saying here, I'm not saying that you can't plug in negative numbers. You can't plug in 0, you can't plug in 1. All I'm saying is that in order for something to be called an exponential function, this number here, the base, is not allowed to be a negative number. It's not allowed to be 0. It's not allowed to be 1. So let's try to see what would happen if we made an exponential function with a negative base. So let's say we tried to make a function that was negative 4 to the x. So what would happen if we tried to plug some numbers into this? So for example, let's try to plug in 1/2, right? Because we want to make and we'll see this in a little bit, that exponential functions, actually their domain is all real numbers. So you should be able to plug any number you want into an exponential function. So what would happen if we tried to plug in 1/2? Well, we would get negative 4 to the 1/2. So what's another way of writing that? Well, that would be the square root of negative 4. Now, we've learned how to express the square root of negative 4, right? We've learned that that would be plus or minus 2i, or I guess actually, sorry, I should just say 2i. However, that's not a real number, right? And so basically, unless we're specifically focusing on complex numbers, for like 99% of this class, we're only dealing with real numbers. And so with exponential functions, we want the inputs and outputs to be real numbers. So the problem is that if you try to make an exponential function where the base is a negative number, you're not going to be able to plug in every number you want. There would be some numbers that would work, right? You could do -4 squared, you could do -4 cubed, you could do -4 to the 0 power, but you couldn't do -4 to the 1/2 because you would get an output that's not a real number. So basically, if you try to make your base a negative number, it's just not going to allow you to plug in every number you would want to. And so that means that we can't define an exponential function to have a negative number as its base. Okay, what about if we tried to make an exponential function where the base was 0? So 0 to the x. So this one isn't as bad. It actually is a function, it works, but it's just not an exponential function. So what do I mean when I say it's not an exponential function? Well, what happens when we plug different numbers into this? So like what happens if we plug in 1, for example? So what is g of 1? That would be 0 to the 1. So what does 0 to the 1 mean? That means you're multiplying 0 with itself one time, so the answer would just be 0. What happens if we plug in 2? Then we would have 0 squared. So what is 0 squared? 0 squared is 0. What would happen if we plug in 3? We'd have 0 cubed, which is 0. So the problem is that this is actually just a constant function, right? It's not really an interesting function because if the base is 0, then no matter what number we plug in, we're always going to get 0 as an output, and that's just not, that doesn't fit what we want an exponential function to be. We already have a name for that. That's called a constant function, so we don't need to discuss it as an exponential function. And then something really similar happens if we try to make a exponential function with a base of 1. So if we make an exponential function, that's 1 to the x. So no matter what number we plug in, so let's say we plug in 1, that's 1 to the first power. So what's 1 to the first power? That's just 1. Any number to the first power is just itself, right? Because it just means that you just have that number multiplied with itself only once. The number is only appearing one time. What about h of 2? Well, that would be 1 squared. And what is 1 squared? 1 squared is also 1. What about 3? That's 1 cubed, 1 times 1 times 1, that's also 1. And so no matter what number you plug in, you're always going to get 1. So this is actually still a constant function. So if this is confusing to you, I don't want you to worry about it too much. It's really just kind of like a technicality. But that's the reason that we're requiring for a to be a positive real number and for it to not be equal to 1. It's because if you try to make an exponential function with a negative base, funny stuff happens. You get some outputs that are not real numbers. And then if you try to make your base 0 or 1, it's just really boring. It's just not an exponential function. It's a constant function. Okay, so now that we've gotten that out of the way, let's actually look at some examples of graphing some exponential functions. So the ones that we're going to focus on is we're going to do 3 to the x, and we're also going to do 1/3 to the x, because by looking at these two graphs, 3 to the x and 1/3 to the x, that will give us a good idea of what are the different kind of shapes that an exponential function can have. So I would encourage you to pause the video and try to fill out these tables yourself and sketch the graph. And then, when you get to the values that are beyond what's on the table, think about where the graph would continue to go. What direction would it kind of point in? Okay, so let's start by filling out this table for 3 to the x. Okay, so how would we evaluate this? Well, we're just going to plug in all these different numbers. So for example, for the first input, we get 3 to the -2. 3 to the -2 is 1 over 3 squared, which is 1/9. What about -1? Well, 3 to the -1 is equal to 1 over 3 to the 1, which is just 1/3. All right, now we have 3 to the 0. So I forgot to mention this on our other page about exponent properties, but a good fact that you need to know is that any number raised to the 0 is always going to be equal to 1. We'll see a little bit later like why exactly that is, but for now, just think of it as it's just kind of a fact. It's like a property that is true for any base. any number that you raise to the 0 power, regardless of what that base is, you're always going to get 1 as your output. Then we plug in 1 and we get 3 to the first power, which is just 3. And then finally we plug in 2 and we have 3 squared, which is 9. Okay, so let's start by plotting these points. So we have -2 1/9. That's going to be really hard to draw. I'll just kind of draw it very close to 0 because it's a very tiny fraction. -1, we have 1/3, so that's something like this. At 0, we have 1. At 1, we have 3. And at 2, we have 9. Okay, so I'm going to connect the dots of what we have so far, and then we'll talk about kind of like where this graph is going to continue to head. So first of all, let's talk about on the right side. So where is this graph going to keep going to the right? Well, it's going to keep going up and up and up, right? And it's going to keep getting steeper because if you think about it, every time we're multiplying by 3 again, right? So we have 1 times 3 is 3, 3 times 3 is 9. Then we're going to do 9 times 3, that's 27. 27 times 3 is 81. So these numbers are going to grow really, really quickly. So the graph is going to be really steep up on the right side. What about on the left side? So what's going on here? Well, for example, if we plugged in -3, we would have 3 to the -3, which is 1 over 3 cubed, which is 1 over 27, which is a really tiny fraction. So basically, the more and more negative the number is that you plug in, the tinier and tinier the fraction is that you're going to get as your output. Now, is the output ever going to go below 0? So is there ever going to be a number that we can raise 3 to where we'll get a negative output? No, right? The output is never going to be negative, and it's also never going to be 0, right? What number could you possibly raise 3 to and get 0? Nothing, right? Maybe your guess would be 0, right? 3 to the 0, but we already know that anything to the 0 is 1. And so there's just no way that your output is ever going to be 0 or it's ever going to be negative. And so what's going to happen is you're going to have a horizontal asymptote. So the graph is going to get very, very close. It's kind of hard for me to draw here, but it's going to get closer and closer to 0 while never actually touching a height of 0. So we have a horizontal asymptote to the left side only. So you might remember when we were talking about rational functions, I mentioned that in the future we'll see some examples of functions where there's an asymptote only on one side. And so this is an example of that. So on the right side, it goes up and up and up. On the left side, it kind of flattens out and never crosses the x-axis, but gets closer and closer to the x-axis. Okay, so let's now compare that to the graph of 1/3 to the x. So first thing we're going to do is we're going to do 1/3 to the -2. So this is where that kind of trick I talked about earlier will come in, where when you're raising a fraction to a negative power, the easiest way to do it is just to take the reciprocal of the number of the base. So in this case, that would be 3, and then raise it to a positive. So 3 squared, which is 9. Or you could do 1 over 1/3 squared, and you would have 1 over 1/9, which is 9. So you'd get the same answer if you wanted to do it a different way as well. What about -1? Well, 1/3 to the -1 is going to be, again, the reciprocal of 1/3, which is 3. 3 to the first power is 3. Okay, next up we have 1/3 to the 0. So any number, regardless of if it's a fraction, a positive number, a negative number, whatever, any number to the 0 is always going to be 1. Next we have the first power, so 1/3 to the first power, well, that's just 1/3. And finally, we have 1/3 squared. So 1/3 squared is 1/3 times 1/3, which is 1/9. Okay, so let's go ahead and plot these points. So we have the point -2, 9. We have the point -1, 3. We have the point 0, 1. We have the point 1, 1/3. And we have the point 2, 1/9. So I'll connect those dots, and then again, we'll talk about kind of like where this graph is heading. Okay, so what about on the left side? So where is Sorry, I'm trying to get that to come out a little better. There we go. Where is this left side of the graph going? Well, because of this kind of reciprocal thing, it's going to go higher and higher the more negative the number you plug in, right? Because what it basically amounts to take 1/3 and raise it to a negative number is the same as taking 3 and raising it to the positive of that number. And so that means that this graph is going to keep going up and up the more the negative is the number that you plug in. And what about to the right? Well, if you take 1/3 and keep multiplying it by itself, the outputs get smaller and smaller, right? We get 1/3, 1/9. The next one would be 1/27. The next one would be 1/81. So the outputs are just going to get smaller and smaller and smaller. Oops. But just like with the other one, it's never actually going to equal 0. It's just going to get closer and closer to 0, right? Because if you think about it, if you keep multiplying 1/3 with itself over and over, it's going to get smaller and smaller, but it's never going to equal 0. It's never going to be negative. You can never get a negative number by multiplying 1/3 with itself, right? That just doesn't make sense. And so again, we're going to have a horizontal asymptote at x is equal to 0, or sorry, at y is equal to 0. Okay, so I want to talk about what these two graphs have in common and then what's different about them. And we'll go to another page to kind of write down some general facts about exponential functions. So let's start with what these have in common. So let's start by talking about the domain and range. So what is the domain and range of these functions? So I mentioned this earlier. The domain of an exponential function is always going to be all real numbers because you can take a number and raise it to any power. As long as that base is a positive real number, you can raise that to any exponent you want and you'll get a defined answer, right? You can raise it to a negative power, you can raise it to a fractional power, you can raise it to a positive power, you can do whatever you want, you're gonna get a well-defined output. So domain is all real numbers. We can also see that on the graph, right? The domain on both of these covers all x values. It keeps going to the left, keeps going to the right. So what about the range? Well, the range is going to cover everything from 0 upward, right? If we look at this graph, it starts at 0, and then it just keeps going up and up and up and up. Now, the range is not going to include 0, right? Because we know that this graph is never actually going to touch a y value of 0. And so let me go to this other page and start to write this stuff down. So like I said, this is going to be, we're going to write down some facts that are true for any exponential function of the form f of x is equal to a to the x. So first thing we said, it's always going to be true that the domain is all real numbers. And so I'll kind of put a note here explaining why that is. So in this case, it's because you can raise a to any real number, right? There's nothing's going to go wrong by taking your base and raising it to a different exponent. Then we talked about how the range, it's from 0 to infinity, not including 0. And so I'm going to kind of explain over here why it is that we don't include 0. It's because if a is a positive real number, a to a power cannot ever equal 0, right? You can't take a positive number and raise it to an exponent and get 0. And that's why the range starts at 0. Okay, what else can we talk about that these two graphs have in common? Well, let's look at the intercepts. So what about the y-intercept? So notice that these both have a y-intercept of 0, 1, right? They both cross the y-axis at a y value of 1. And so that's going to be true for any exponential function. So they're always going to have a y-intercept of the point 0, 1. And that's, as we mentioned, that's because a to the 0 is going to be equal to 1 for any number a. So, how do you find the y-intercept? Well, it's what you get by plugging in 0 for x. And so if you take a number and raise it to the 0, you get 1. So other thing I want to talk about, and I just realized I think I need to, let me just move these down a teeny bit. We're going to draw like a general shape for a couple of different cases. But yeah, so what about x-intercepts? So notice that these functions, neither of them has an x-intercept. And why don't they have x-intercepts? Well, like we said, it's because they have a horizontal asymptote at y is equal to 0. So both of these are going to have a horizontal asymptote at y is equal to 0. And one thing to mention is that that horizontal asymptote is only on one side. And depending on what your exponential function is like, it could be on the left or the right. And we'll talk about that in just a moment. So why do we have a horizontal asymptote? Well, it's actually basically the same reason as what we wrote for the range. So it's basically because a to the x cannot equal 0. So I'll just say it a little more briefly here. But basically it's because a is supposed to be a positive real number, so a to the x cannot equal 0. But what will happen is the function is going to approach 0. But I'll say it this way, but a to the x will, sorry, my screen's a little stuck. There we go. Approach 0. And I'll just leave it at that because it's going to depend on which type of function we're looking at. It depends on, well, we'll see in a second, but either the function will approach 0 to the left or to the right. Because it will get, in the example here, as we plugged in more and more negative numbers, the graph got closer to 0. But if we look at the example here, as we plug in more and more positive numbers, the graph gets closer to 0. Okay, so that brings us to our next question, which is why do these, what's different about these? So you might notice that these two graphs are actually just kind of flipped from each other, right? They're reflected over the y-axis. And that's something we'll actually talk more about in the next video when we talk about transformations with exponential functions. But for now, what I want to focus on is just kind of the general shape. So notice that for this one, for the first one, 3 to the x, the graph has a horizontal asymptote to the left and it gets bigger to the right. Whereas for the one that was 1/3 to the x, we have a horizontal asymptote to the right and the graph gets bigger to the left. So what do you think it is? Like, what is it about 1/3 to the x versus 3 to the x that causes them to have these different shapes? Like, what would we want to change the base to? Or like, what is it about these bases that makes them have a different shape? So it's really about how big that number a is. So if your number a, if your base is bigger than 1, you're going to have a shape that looks like this one. Your graph is always going to get bigger from left to right. So why is that? Well, if you think about it, like imagine you had 2 instead of 3. You would have 2 squared, 2 to the third, 2 to the fourth. As you multiply 2 with itself more and more, it gets bigger and bigger. Right? If your base is already bigger than 1, if you keep multiplying it with itself, the outputs get bigger and bigger. And so that's why on the right side, it goes up and up and up. Now, why does it go down on the left? Well, that's because taking a number that's bigger than 1 and raising it to a negative number, you get these fractional outputs. Whereas with 1/3, well, 1/3 is smaller than 1. So if you take a number like 1/3 and multiply it with itself, the results actually get smaller, right? 1/3 times 1/3 is 1/9, times a third is 1/27, times a third is 1/81. So like the more you multiply it with itself, the smaller it gets. And then why does it go up on the left? Well, it's because of this reciprocal thing that happens with the negative exponents. So the general rule to know is going to be that we have two kind of shapes here. So the two shapes are going to be, the first case is if A is bigger than 1. So if your base is bigger than 1, you're always going to have a shape of a graph that looks something like this, where it passes through at 0, 1. And then if your base is less than 1, maybe I'll use a different color. I wanted to match it with the past page, but I think I'm already using that purple color for something else. So if your base is less than 1, the shape is always going to look like this. So let me just show you something on Desmos to really drive that point home. So here I have graphed f of x is equal to a to the x, and I put a slider on a, which means I can just try different values of a. So currently it says a is equal to 1. Notice that that gives me a horizontal line. So that's why we did not call this an exponential function. So now I'm going to drag a to the right. So I'm going to make a bigger and bigger. And so notice how the graph just gets steeper and steeper, right? The bigger the base is, the steeper the number is going to get. But as long as a is bigger than 1, it always has the same shape. Even if I go down to like a is equal to 1.1, right? It still goes up to the right and it eventually flattens down to the left. So as long as your base is bigger than 1, it's always going to have that same basic shape. Now, if I pull a to be less than 1, that's where we're going to start seeing that flipped shape, right? Where it's going up to the left and down to the right. And so notice that if a is less than 1, now actually the smaller that a gets, the steeper the graph gets. And it's basically because of that whole reciprocal thing that happens with the negative exponents. Now, look now, if I go back and forth, one thing you might notice is that y-intercept stays the same, right? That's because 0 to any power, or sorry, any number to the 0 power is 1, right? So that's why you always have this y-intercept at 1. And now what do you think is going to happen if I try to make a negative? Well, the graph just disappears, right? Because we talked about how an exponential function just doesn't even make sense if the base is as a negative number. So we're now going to be kind of adding this to our list of basic functions whose graph shapes I want you to know is these exponential functions. So the main thing I want you to know is this picture here. I want you to know that if your base is bigger than 1, you're going to have this shape where it grows from left to right. If a is less than 1, you're going to have the shape where it goes down from left to right. And I want you to know that the y-intercept is always 0, 1, and that you always have a horizontal asymptote only on one side. So the exponential functions are never going to be negative. They're always going to approach 0, but never actually get smaller than 0. All right, so that is it for this video. In our next video, we're going to be practicing a little bit more with graphing different exponential functions and transformations. So I'll see you all in our next video.